In this clip I'll not go through anything new. I'll simply give a graphical representation of probability. I like to give algebraic proofs, but for some it may be easier to think graphically. The mathematics here will be pretty sloppy. I'll concentrate on keeping it as simple as possible rather than going for complete accuracy. I'll start by reintroducing the Venn diagram, which shows a set, let's call it A. The set depicted does not contain all possible elements, which is why you see stuff outside the blob. The entire screen represents all possible elements. I'm going to take a set theoretical approach to probability now, but see the clip on set theory and logic to see the interconnection between the two topics. The elements in the universal set, the set of all possible elements, represents the possibilities that you wish to consider. And here's a refresher. An intersection of set A and B contains the elements which is in set A and in set B. So intersection represents the logic and operation. The union of A and B contains the elements that are found in A or B or both. So union represents the logical OR operation. The complement of A is the set of elements that are not in A. So the complement represents the logical NOT operation. Subset A of B is a set where being an element in A implies being an element in B. So a subset represents a logical implication. The two sets A and B are the same if B is also a subset of A. So two sets being the same represents logical equivalence. Now I'm going to abuse the Venn diagram by not only drawing the sets as rectangles or other sharp shapes, but by letting their area relative to the total screen represent the probabilities. The larger the area, the larger the probability. Probability 1 will fill the entire screen, while probability 0 will be nothing, an empty set. Think of an outcome as drawing a point on the screen randomly, with equal probability for each spot. If you are choosing such points many times, the number of points inside the area should then be proportional to that area. The rate of points inside will be the probability. Now let's review the three basic rules of probability. Rule 1. The probabilities are between 0 and 1. That's a check, since a probability of set A will be represented by the area covered by set A divided by the total area. And we can define the total area to be 1. Rule 2. The probability of A plus the probability of not A is equal to 1. The set of A and the complement will cover the entire set represented by the screen. And the area should then sum to 1, so that's okay. Rule 3. The probability of A and B can be written as the probability for A given B times the probability for B. As stated in clip 2b, a conditional probability of A conditioned on B can be said to zoom in on the set B. B can be said to be the new universal set, the set of all possibilities now, that is conditioned on B. Multiplying the probability of A given B with the probability of B will then zoom out to the old universal set and look at the probability of A and B. Dividing the probability of A and B with the probability of B will thus zoom in again. Of course we could do the same operation on A instead. So the probability for A and B is the probability of B given A. So you then zoom in on A and look at the probability for B times the probability of A, so then you zoom out again. If you have an observation D and wonder what the probability for model M is now, i.e. the probability for the model M given data D, we start off with the probability for the data D given the model M. We start here because the role of a model is simply to describe such probabilities. If you do not have the probability of the outcomes given a model, you do not have a model. So we start there and now zoom out by multiplying that probability with the prior probability for model M. We then zoom in on the actual observation by dividing with the probability for the data. And now we got the probability for the model given the data, and that's Bayes' formula. If you've seen the previous clip, you may remember that in there we assumed an implication A implies B, and then we wondered what happened with the probability for A if we observed B. The claim was that the probability for A would increase. It was also claimed that the probability for A prior to the data was smaller than the probability for B if A and B were not equivalent. This may now be fairly easy to see. As I mentioned, A implies B is represented by A being contained in B, and equivalence by A being equal to B. So if A implies B but A and B are not the same, then there are elements in B that are not contained in A, and with possible probability for these elements, the probability for B is larger than the probability for A, i.e. the area is greater. Now, by conditioning on B, we zoom in on B, and since A is contained in B, it's easy to see that the area of A has now become larger relative to the full screen. We zoomed in by dividing the original probability of A and B with the probability for B. So since A and B is equal to the set A, the probability for A is now larger. For instance, the probability for it raining without any more info will be smaller than the probability for it raining if it's overcast. So if you learn that it's overcast, the probability for it raining will increase. Let's go through the three other general probability rules too. Rule number 4. The probability of a union of mutually exclusive events represented by set B1 to Bk is the sum of the individual probabilities. Using our graphical representation, this is not hard to see. The area covered by the union set is the sum of the individual areas, since there's no overlap. Rule 5. The probability for A or B is the probability for A plus the probability for B minus the probability for A and B. The reason for the set minus the probability of A and B is that this area is counted twice. Once when we add the probability for A and once when we add the probability for B. Rule 6. Here we first need a graphical representation of a partition. A partition is a set of mutually exclusive, that is, disjoint sets that span the universal set. Usually the partition will be made out of disjoint collections of models. In this picture there are 4 different models. The probability for anything else, such as the dataset D, is then the probability for the data and model 1 plus the probability for the data and model 2 plus the probability for model 3 and the data plus the probability for model 4 and the data. Or it's the probability for the data given model 1 zoomed out, that is multiplied with the probability for model 1, plus the probability for the data given model 2 zoomed out, plus the probability for the data given model 3 zoomed out, plus the probability for the data given model 4 zoomed out. And that's the most advanced rule I will show here. It may be an advantage to be able to think graphically and not just algebraically. So this representation does not form the real tools for probability theory. This is just a representation.